Hello everyone and welcome to the 7th 3D Buzz Math VTM. My name is Rob Rolnick, known on 3dbuzz.com simply as Dimondo. And with me tonight we've got
Logan Frank.
Excellent. So in lesson number 7, we're going to continue with our talk about geometry. Except now we're going to jump out of the world of polygons and into the world of circles. So we'll start by just giving you the answers to the questions asked at the end of lesson 6. And what I'm going to point out, though, is that it's important to realize that when you're doing areas, you're talking about units squared. So if your measurements are in centimeters, centimeters squared. If your measurements are in yards, yards squared, and so on. So anyway, although a circle is technically not a polygon, as the number of sides of a regular polygon increases, its shape gets more and more circular. So you might not notice when jumping from a triangle to a square, but as you look at the pentagon and hexagon, you'll notice that they're getting increasingly circular. In fact, if you had 100 sides, it would look even more circular. 100,000 sides, more so still. A nice way of thinking about this is thinking back to Logan's example of taking a regular polygon and saying you can hit all of its vertices in a circle circumference. Well, that just makes sense that as the number of vertices increases, since they're all going to be equally spaced apart,
the shape will start to resemble, or more and more start to resemble a circle. Exactly.
So a circle is formed by taking all points that are a fixed distance away from its center.
But I guess one key thing to remember is you never really can make a true circle by making a polygon with infinite sides, because you don't have any real way of representing infinite sides on a polygon.
Right. In calculus, you could say the limit as the number of sides approaches infinity. But you can't say when the number of sides is infinity, because that can't happen. Which is why they invented the handy protractor tool that you can use for drawing circles.
Right. When you're defining a circle, you're more strictly talking about the points defined at a fixed distance around its center.
Right. You'd say something really technical, like the locus of all points formed when as you rotate a line segment along its endpoint, or something stupid like that. The important thing to realize is that you have a certain distance, and if you rotate that distance, the path it takes will be a circle. So in real life, imagine you had a yo-yo and you're yo-yoing and the yo-yo drops and you don't pull it up, right? Because you're like me and you suck at yo-yoing. And then you get all frustrated and you start spinning the yo-yo around your head. Well, since the length of the cord is fixed, as the yo-yo spins, it's spinning at a fixed distance from the center of the cord, well, where your finger is attached to the cord. And as such, the path the yo-yo takes will be circular.
Which makes sense, because if the string can't adjust in length, that means that the yo-yo is going to trace out the path of the circle.
Right. It's also important to realize that all circles are similar because of how the definition is worded. Since it's always all the points taken from a fixed distance from the center, as you increase or decrease that distance, you'll increase and decrease proportionally the size of the circle. Terminology. So, what's important to realize is that when talking about circles, there's loads and loads of terminology. None of it is complicated, none of it is hard or confusing. It's just a lot of words. So I'm going to guide you through it with Logan's help. So, the radius. The radius is a line segment that starts at the center of a circle and goes to its circumference. So the point O is generally used to represent the center of the circle. And at O, which would be here, because that's where this intersection takes place, and the radius stops, is the center. You go from there to the circumference, which is the outer perimeter of the circle, and that's a radius. If instead, though, you could get a diameter, if you started at the... actually, I'll just read it. Diameter. A line segment that passes through the center of the circle, and each end ends on the circumference. So essentially, it's as if you took a radius and just continued until it hit the other side. So something like that. Then the radius becomes a diameter. And as such, it might be kind of clear that a diameter is always twice the length of a radius.
Right. 2 times the radius is always going to equal the diameter.
Exactly. Terminology Part 2. A chord is a line segment joining 2 points on the circle's circumference. So you'll see that here, and you might have noticed on the previous slide, I color-coded. So the red chord here joins this point on the circumference and that point. Using this logic, you could say that, well, the diameter is a chord, and it also happens to be the longest possible chord. A secant. A secant is a line that cuts through the circle, as you can see. It's essentially a chord that isn't a line segment. It just goes on in both directions. Whereas a tangent is a line that touches the circle, but does not cross through it. So imagine you had, like, a circle, and you were balancing a pencil on it, or something like that. The pencil would be tangential, or would be tangent to the circle, because it's balancing on it, but doesn't cross through it.
Right, it's simply a line that rests on the edge of the circle.
Exactly. Terminology part 3. Circumference. A circle is equivalent to a perimeter. So whereas in a polygon, you'd say, well, the perimeter of the polygon is something, 17. The circumference of a circle is also the same, it's the same equivalent. So you could say the circumference of the circle is 3 units. Central angle. An angle formed by 2 radii. So you'll see that there's one blue radii here, and a second blue radius here. And the angle between them, you usually do the smaller of the 2 angles unless explicitly stated otherwise. When you're talking about the central angle, you almost always take the smaller angle, not the outside one. This angle x is the central angle, because it's formed between the intersection of 2 radii. Whereas an interior angle is an angle formed by 2 chords which intersect on the circle's circumference. So you'll see there's 2 purple chords, and the angle here, y, is the interior angle. Does that make sense?
Yeah, simple enough.
Excellent. It's also important to note that so long as you're staying outside of this area here that I just circled, or ovaled, so long as you're outside of that, if you took the same endpoints of these chords and made them intersect somewhere else, so like this, then the angle here would also be y.
So regardless of where you make an interior angle, as long as it's outside or basically on the outside edge of where you drew the, where you'd circled, where the 2...
yeah, the arc it subtends. So long as you're, that's the vocabulary for it. So long as you're outside of the arc that it's subtending, that's, staying inside of it,
then the angle will always be the same.
Exactly. And so let's move on to part 4. Arc. Any portion of a circle circumference. The key word there is portion. Once you take the entire circle circumference, well, you have a circle.
Right, you're talking about a whole circle. I guess there's no such thing as a 360-degree arc.
Right. So if you, let's say you had something that was almost a circle, but like that, so you have that little bit area that's not connected, then yeah, that's an arc. But once you connect that little area, then now you've got a circle.
Now we're talking about a circle.
So, a minor arc. A minor arc is an arc which is less than or equal to 180 degrees. Because essentially you relate the arc to the angle from the central angle. You can relate them.
Which basically means that a circle would be 360 degrees.
Right. So you can see here that this is definitely less than 180 degrees, because 180 degrees, as you may remember, would be a straight line. And as such, the corresponding arc is considered a minor arc. On the other hand, a major arc is an arc which is greater than or equal to 180 degrees. So namely, an arc that correlates to this part that I'm circling in red.
So that would be a major arc. So from that I would take it that if you had an arc that corresponded to half of the circle, that would also be a major arc. It
would also be a minor arc. You don't really... Some people say that it should not be less than or equal to...
So this gets into another one of those discussions where, depending on how you go about looking at it, it could be either or.
Exactly. It's depending on your point of view. So some people say, well, if you're dealing with 180-degree arcs, then immediately it's no longer major or minor. It doesn't fall into these categories. So other people say, well, it depends on your point of view. It could be major or it can be minor, depending on what you're talking about.
So to keep things simple, we'll just say that a minor arc is less than 180 degrees and a major arc is greater than 180 degrees.
Yeah, you can think of it like that. Or me, I just say less than or equal to. It doesn't matter. It's the same thing. Okay, so a circular segment. The area contained between a chord and the minor arc formed when the central angle has the chord's endpoints. So, it's pretty simple. You have a chord here, right there. I just circled it, or whatever. And you have... actually, yeah, sure, I'll just keep all the ink. I was thinking it might be getting a little cluttered, but whatever.
It's fine.
You have 2 radii connected to the endpoints. And this area in green that's kind of outside of the triangle formed by the chord and the radii is considered a circular segment. Meanwhile, a circular sector can be thought of kind of like a piece of a pie. So it's the area contained between a minor arc and a central angle. So here's your minor arc, labeled X. And here's your, there's your central angle, labeled X. Your minor arc is also in red. And the area between them is your circular sector, in blue. Terminology Part 5. This is the last of the terminology. Concentric circles. There are multiple circles sharing a common center. So, all of these circles are concentric with one another. The red one, the orange one, the yellow, the green, and the blue. And I guess that little black dot that was supposed to represent the center is also concentric. Radius and degrees. So many people get confused when talking about radians and degrees. Radius and degrees. Yes. No. It should be radians. Radians and degrees. The easiest way I can explain that is like this. When you're making a measurement, you can measure things in miles or kilometers, like when you're driving. You can measure a football field in meters or yards, and so on. So they're basically, radians and degrees is the same relationship. It's 2 separate, distinct ways of measuring angles. So they're both ways of measuring angles, and the easiest relationship between them is that a semicircle, so something that would look like that, semicircle, a dome, has 180 degrees or pi radians. Pi being 3.141592654, etc. So here are some other relationships. 30 degrees is pi divided by 6, because that's 1/6 of 180 degrees. 45 degrees is a quarter of 180 degrees, so it's pi divided by 4. And so on and so forth for the others. If you had to find, let's say, the amount of radians in, 37 degrees, then you can use this formula here. You say, you're essentially making equivalent fractions. You say pi divided by 180 equals, I think I said 37 degrees?
Yes, that's correct.
37 oops.
Yeah,
Hang on, let me grab the eraser tool for a sec.
The radian side of...
Yep. So pi radians over 180 degrees is equal to an unknown amount of radians over 37 degrees. So now you ignore that little y that I just wrote over. And then you have to solve for x, because that's the amount of unknown radians. So you multiply both sides by 37, and you get 37 degrees divided by 180 degrees. That's an 8. I'm sorry, that's a little sloppy. Times pi, equals x. And you plug that into your calculator, and suddenly you can figure out how many degrees is equal, how many radians is equal to 37 degrees.
So really it's very simple to convert back and forth.
Right. And similarly, if you want to solve for how many degrees are in 1 radian, you'd say something like pi divided by 180. You want 1 radian, so 180 degrees equals 1 radian divided by y degrees. You solve for y, which basically means you multiply both sides by y, and you'll have pi divided by 180, y equals 1. And then you multiply by 180 divided by pi, and you'll get 1 radian is equal to 180 divided by pi, which is like 50-something. I'm going to say ish. Maybe 56 or 57-ish. I'm doing that in my head, so it's probably wrong. In any case, let's move on. Properties of circles. So the circumference of a circle is 2 times the radius times pi. And the diameter of the circumference is also the diameter times pi. And that's because 2 times the radius, as we said earlier,
is the diameter.
So that's really simple. Pi is just the relationship between a circumference to the diameter. Whereas the area of a circle is pi times the radius squared. And again, just work out the radius squared. So if the radius was 5, you'd have 25 times pi.
Simple enough.
Again, area would be units squared. So now we'll move on to some other properties of circles. This one is known as central and interior angles. So from this point forward, in all of these examples, we're going to assume that the radius of the circle we're dealing with is 1. If the radius is 3, then it's not too bad because it's a similar circle to the radius of 1, and every value is just multiplied by 3, and so on and so forth. And we're also going to assume that we're working in radians. So here you see 45 degrees. You just use the methods we talked about earlier and convert that to radians, and you're good to go. So the length of an arc subtended on a central angle is equal to that central angle. So that's kind of clear to see. If you have a central angle, in this case 90 degrees, or pi halves radians, then this arc subtended on it is also pi halves radians. And that's kind of obvious, because if you think about it, 180 degrees is how many radians?
That would be 1 radian.
Pi radians.
Oh, yeah. 180 radians, yeah. Yeah, pi radians.
180 degrees is pi radians. So 90 degrees is pi half radians. And therefore, this, we know is pi half radians, and the way we know that's also the length of the side is simple. Simple. You simply say the circumference is 2 pi r, 2 pi times radius, and we're assuming the radius is 1. So the circumference is 2 pi. We want a quarter of the circumference, because we're looking at a quarter of the circle. So you divide by 4, and that becomes pi halves. So we just showed that the amount of radians corresponding to 90 degrees is pi halves, and the amount of the length of the arc is also pi halves.
Very nice.
So that's why it's important to work with radians. If you're working with degrees, you can also say it's 90 degrees, the length of the arc, but generally you don't measure lengths in degrees because it kind of gets confusing quick. Meanwhile, the size of an inscribed angle is half the size of the arc it subtends. So here's the inscribed angle right here. And I'm saying it's 45 degrees. And that would be half of 90 degrees.
Makes sense.
And now we're going to give a proof to that. So here we have a central angle. And here we have an inscribed angle. So we can look at all of this and, go, how would we realize that the inscribed angle is half of the central angle? Well, I'll erase all the ink on the slide and then show you. We have 2 triangles. We have triangle A, B, O, and we'll deal with that for now. And then we'll talk about the other triangle, AOC. Well, the important thing to realize is that triangle ABO is an isosceles triangle. If you recall, that means 2 sides have the same length and 2 angles are equal. So we know this angle, which I'll label X, and this angle, which I'll label also X, are equal. And this angle, which we don't know, so I'll call that A. Well, we don't know what A equals. But actually A is a bad choice, because we have ABC. I'm going to label it alpha. We know alpha is equal to 180 degrees, or the total amount of degrees in 180 degrees, which is the total amount of degrees in a triangle, minus 2x. Right?
Yep, that's right.
And so we also see that triangle AOC is an isosceles triangle, this length being y, and this angle being y, that angle being y, this angle labeled beta. We don't know what it is, but we also know similarly that beta equals 180 degrees minus 2y.
Okay.
Now, we want to know angle, and I'm going to just say that we want to know this angle here for O. But we don't really know that anything about that angle. But if we took a full 360 degree angle, then we know that O is 360 degrees minus alpha minus beta. Right?
Right, because alpha and beta are the only two other angles taking up the
360 degrees space.
Degrees.
Right. So we can say that the angle BOC equals 360 degrees. I'm going to stop writing a little degree symbol just because it's hard to write. But in practice, always write degrees. Minus 180 minus 2x minus 180 minus 2y. And if you work this all out, you're going to find out that that equals 2x plus 2y by distributing the minus sign, which equals 2x plus y. Right?
Yep.
So that's what now we know that the angle O is 2x plus y, like 2 times x plus y. So 2x plus 2y. We also know this interior angle is x plus y, because it has half of one part of it is x, the other part of it is y. So if the interior angle, int, is equal to x plus y, right? That's what the interior angle is. And the central angle, is equal to 2x plus y, well then it's quite obvious that the interior angle is half of the central angle.
Yep.
And that's how we can prove the what we were trying to show. And the proof, it might be a little hard to read because I'm writing all sloppily on a tablet. But if you watch the slide 2 or 3 times, you should understand the proof.
Yeah, I mean, it all makes sense. It's a fairly simple process to follow all the way through.
Right. So moving on. Chord interception. To find an angle, so meaning the angle, one of these angles that are at E, so either AED, BEA, or any of the others, you simply add the arcs subtended by opposite angles and divide by 2. So this might sound very confusing and complicated. It's not. What I'm trying to say is this. We know angle AED over here is equal to angle BEC because they're opposite angles. And we talked about that in a previous lesson. Well, if those two angles are equal, then by the theory here, that's also equal to a half of the arc. See that little slope, arced line over AB? That means you're looking at an arc, not a straight line between A and B. So you're looking at the arc AB, which is AEB is the arc AB here, plus the arc CD at the bottom. The D might be a little cropped based on our viewing area, but it's this area here. D is down here if it's cropped in the video. And you divide that by 2. You add the arc lengths, divide by 2. Similarly, angle AED equals angle BEC, which is a half of the arc BC plus AD. So, just memorize the formulas. Chord tangent interception. An inscribed angle is half as large as the arc it subtends. So you can think about this a lot like chord angles with interior angles. Let's say you knew the length of this arc in blue to be 90. I'm not going to say 90 because I should stay consistent. I'm going to say, let's say you knew that it was pi, I don't know, I'll say pi thirds. I don't know if that's a really realistic value or not. Let's say you knew that that was pi thirds, which is really ridiculous because pi would be half of it. But let's just assume this made sense, and that value was realistic.
Right. Figure not drawn to scale.
Right. So assume that this whole arc is pi thirds. Well, then the angle here, ABC, angle ABC, is half of that. So pi thirds divided by 2 is pi sixths. So that's all this is. If you know the arc that it subtends, then the angle is half of that.
It's really just a very simple property.
Right.
Chord, tangent, interception.
And similarly, so this half would be 2 pi. The other half, the black arc, would be 2 pi, the entire circumference, minus pi thirds, minus the part in blue. So that would be, 5/3 pi?
Something like that.
So I'll assume it's 5/3 pi. Which equals 5/3 pi. Which means the other side, let's say I had a D up here. Angle CBD is 5/3 pi divided by 2, which is 5/6 of pi, times pi. And there you go. But that also brings up another point. If we know that angle, we just showed that angle CBD is 5/6 pi. Well, what happens if you add up angles ABC and CBD, Logan?
You would get a supplementary angle, wouldn't you?
Yeah, 180 degrees. And that's pi radians, and that's exactly what we expected. So that's obviously this isn't a proof of the theory, but it shows that it makes sense.
It's showing that the other side of it matches up.
Right. Exterior angles, secant interception. Well, you can see that we have 2 secant lines, and they intersect. Wow, I keep saying interception. I probably should say intersection, but I'm Canadian. So anyway, so all of you who are going to say, look, you spelled it wrong. Yeah, I realized while we were recording, I'm just not going to re-record this video. So if you think it should be intersection, more power to you. So anyway, the important theory here is that angle ACE, meaning this angle here, is equal to a half of the arc EA minus the arc DB. So this concept of subtracting 2 arcs and taking a half of it follows through to the other exterior angle theorems. So if you're doing a secant tangent interception, the angle ACD, located here, is simply this big arc AD minus the small arc BD, and divide that by 2.
So it almost follows the same rule as though both lines were secants instead of one being a tangent.
Exactly.
They follow the same rule.
And in fact, it follows the same idea if you're doing tangent intersection. You take a half of the big arc, in that case it would be BC going this way, minus a half of the small arc, BC going this way, and divide by 2. Another interesting thing to note is that if you have 2 tangents and they intersect, so they're intersecting here at point A. Well, the distance from A to B is the same as the distance from A to C. So this distance here is the exact same as this distance here. So 2 tangents that intersect each other, from that point to the point where they to the point where they're tangential to where they touch the circle, is the same length. And that was note number 2. Note number 1 is saying that angle BOC is equal to angle it's supplementary to angle BAC. So I'm not going to explain why just yet, because we're going to be talking about why in a future slide, if Logan reminds me to. inscribed triangles, namely this slide. An inscribed triangle is a triangle inscribed inside a circle. Well, it's not this. Okay, rather, a triangle inscribed inside a circle along its diameter will always be a right triangle. So, an inscribed triangle, as you may remember, is any triangle drawn so that its vertices hit the circumference of a circle. If it happens to be that one of the sides of the triangle is along the diameter of the circle, then you'll always have a right triangle. So, Logan, should we prove this first and then go back to the previous slide and explain the supplementary angle thing? Or should we first explain the supplementary angle thing that we already spoke about and then do the proof?
We could do the proof just so that we have everything here in concrete, if you could say. And then we'll go back and show how this applies to the previous example. Okay, that's cool. So, let's do a proof. Well, once again, since I broke it down into a whole bunch of radii, we know that AO, the line segment AO, is a radius. So it's equal to the line segment OB, which is equal to the line segment OC, because all radii in a circle are equal in length. It's important to note that these diagrams are not drawn to scale. So, a triangle inscribed inside a circle along its diameter will always be a right triangle. So here's how we do it. We say, okay, look, we know we're dealing with isosceles triangles, so if this is x, then this has to be x. And then that's one isosceles triangle. Similarly, here's another. So if this angle is y, then this angle is also y. So we have one isosceles triangle, which has the two equal angles of x is AOB, triangle AOB, and triangle COB has the equal angles being y. Those to be the y angles.
Right. So we also have another triangle, the big triangle, which is triangle ABC. Well, we know that the sum of all the angles in the triangle has to be 180. So we can say this: 180 degrees equals angle BAC, which is x, plus angle ACB, which is y, plus angle ACB, which is y, plus angle ABC, which is x plus y. But if you work that out, that's once again 2x plus y is 180 degrees. Divide both sides by 2, and you get 90 degrees equals x plus y. And I didn't do it on the previous proof, but I should have. QED for quadrilateral demonstrandum, and I always draw that little box. So there you go. A lopsided proof. Because I wrote lopsided.
But nonetheless, that's just showing that the inscribed triangle is in fact a right triangle because XY form a 90-degree angle.
Right, so that's a right angle right there. So now that we have this, we're going to backtrack 2 slides, and we're going to say, okay, well, this then is a right angle because you have a tangent and a radius that intersect at right angles. And here's a 90-degree angle, and the shape OBAC is a quadrilateral, which means it has 360 degrees in its internal angles, 2 of which are 90 degrees. So remove both of those. You get 360 minus 90, which is 180. So that means this angle at O here, called X, and this angle here, called Y, which complete our quadrilateral, have to be supplementary.
Oh, very nice. So do we want to move on past the where we did the proof?
Yeah, sure. Because I just want to illustrate that if we had a tangent here...
Okay, so yeah, reconnecting this to the other example.
It would hit the radius at 90 degrees. And if you don't see that right now, that's cool, because it gets really, really clear when you rotate the circle and look at it like this.
Then yeah, any tangent is perpendicular to the radius.
Right. So if you would rotate your circle somehow like that, you'd end up with it looking like this. But it would still be at 90 degrees. So combining this with the other theorem of the interior triangles, and if you go back again, you can combine it all to show that it does make sense with the quadrilateral proof, or theory.
Yeah, this is just showing that those angles where the tangent intersects the circle have to be 90-degree angles.
Not where the tangent intercepts the circle, but where the tangent and the radius.
Where the tangent and the radius intercept, excuse me.
Oh, and here I actually wrote intersection. So, yeah, maybe it is intersection. Maybe it isn't. In any case, I'm Canadian, and I talk funny for all you Americans. So, and for you Canadians who listen to this, and, you're like, why is he criticizing our country? Well, I can. So that's the end of this lesson. You might be curious why there aren't any examples. Well, there's not really much examples to give, because it's all just different theory, and you just need to find out which one applies and apply it to the picture that I'd give you. If you want a little bit of practice, what I would recommend is just picking a couple of degrees at random, converting them to radians, and picking a bunch of radians at random and converting them back to degrees. Or just take one and convert it both ways and see if you get the same value.
Yeah, just to get used to converting that so you're very comfortable with working with the two measurements.
Right, because in calculus especially, you're almost always working with radians. So that's going to wrap up this lesson. I'd like to thank everyone for listening, and thanks a lot, guys.